In this lesson, we're going to talk about the Poisson distribution, not the Poisson distribution. It's like a, how you would say fish in French, so Poisson. It's separated from the binomial and geometric lesson because it's not related to a sequence of independent Bernoulli random variables. So the PDF of a Poisson random variable is the probability that you get k is lambda to the k over k factorial e to the minus k for some lambda bigger than 0. So lambda is the parameter in this case. And if x has a Poisson distribution with parameter lambda, we can write x has the distribution of a Poisson lambda. It's common to use a Poisson to represent the number of events that occur over a certain time interval. So the number of phone calls you get over the next 1 hour time interval could be represented by a Poisson random variable. Or if you're running a restaurant, the number of customers that come over the course of a day is represented by possibly a Poisson random variable. So that's the kind of thing you might use a Poisson random variable to represent. Now we're going to compute the mean and variance just as we did for the geometric and binomial random variables. So let x be Poisson lambda. The expected value of x is, just by definition, the sum from k equals 0 to infinity of k times the probability x equals k, which is lambda to the k over k factorial e to the minus lambda. If you plug in k equals 0, you just get 0, right? So we don't need the 0th term, and we're going to reindex from k equals 1 to infinity instead of from k equals 0 to infinity. Then we can also cancel the k with the k factorial. So this becomes k minus 1 factorial, and that's just because k divided by k factorial is 1 over k minus 1 factorial. And that's how we get here. Then we're going to pull out some constants. So we're going to pull out a lambda and an e to the negative lambda. And since I pulled out a lambda, this is now lambda to the k minus 1 over k minus 1 factorial. And we can re-index the set. So we're going to bring the index down by 1. So instead of going from 1 to infinity, we're going to go from 0 to infinity. Why are we re-indexing again? Well, the first time we weren't re-indexing, we were multiplying by 0. And this time, we're going to shift, instead of going from 1 to infinity, 0 to infinity, but we're not changing the numbers we're adding over. So we need to increase the k's by 1 in the sum, since we decreased the indices by 1. So instead of going lambda to the k minus 1 over k minus 1 factorial, it's lambda to the k over k factorial. And this sum is just the sum for e to the lambda. Right? The sum 0 equals k equals 0 to infinity, lambda to the k over k factorial. So we can plug in e to the lambda, and e to the minus lambda and e to the lambda cancel, so we get the expected value of x is lambda. It's kind of nice because it's really easy to remember. The expected value of a Poisson with parameter lambda is just lambda. Now let's find the variance. To find the variance, we should first compute the expected value of x squared, so we can use the formula e of x squared minus the quantity of e of x squared. So e of x squared is k squared lambda to the k over k factorial e to the minus lambda. And for this one, I'm going to use, we're going to rewrite k squared. So k squared is k times k, which is k minus 1 plus 1 times k. Okay, so just kind of a funny rewrite there. So k squared is k times k minus 1 plus 1, or in other words, 1 plus k minus 1. Then we're going to distribute this k, not the k, the yes, that's right. We do want the k. So the k lambda to the k over k factorial e to the minus lambda. We're going to distribute that to the 1 and the k minus 1. So we have a k times lambda to the k over k factorial e to the minus lambda all times 1 and then we have a k lambda to the k over k factorial e to the minus lambda all times k minus 1. So we distributed it to this part and to this part. Now, this summation here is just e of x. It's the expected value, right? It's k times the probability that x equals k, which we've already computed, and that's lambda. So if we were just to run down these three equations for this sum, the sum is e to the x, which is lambda as computed above. Now for the other part, we're going to have to compute this sum of k minus 1 times k lambda to the k over k factorial e to the minus lambda. And now we can cancel off the k and the k minus 1. But it looks like also I've already reindexed here. So we could sum from 0 to infinity, but when we plug in k equals 0, we have a k here. So that's just going to be 0, and it's going to cancel off everything. So if we plug in 1, well, we have 1 minus 1 in the k minus 1 part. So whenever k equals 1, that's also 0, and that just wipes out everything. So we're only summing from 2 to infinity of k minus 1 times k times lambda to the k over k factorial e to the minus lambda. And then we can cancel two terms. So k factorial with k and k minus 1. Remember that this means 1 times 2 up to, so we'd have a k minus 1 and a k over a k minus 1 and a k, which my handwriting is so sloppy you probably can't read this, but the k minus 1's cancel and the k's cancel. So that's why we're left with a k minus 2 factorial. And then the steps are pretty similar. So we pull out, instead of just a lambda, we'll put a lambda squared, e to the minus lambda. And so the inside is lambda to the k minus 2 over k minus 2 factorial. Then reindex, but shifting by 2. So instead of summing from 2 to infinity, we'll sum from 0 to infinity. And it's lambda to the k over k factorial, which, as we mentioned above, is lambda e to the lambda. These cancel, and so we have lambda plus lambda squared. The variance is e of x squared minus e of x quantity squared, which is this part is lambda plus lambda squared, and e of x is lambda, so we're subtracting that squared. So minus lambda squared just gives us lambda. Therefore, both the expected value and the variance are equal to lambda, which makes this a bit easier to remember than some of the other ones. The expected value and the variance are just the parameter.